Hello everyone, my name is Shimbo. It's my great pleasure here to present our work on hosting capacity analysis using Bayesian optimization. This work is a collaboration with Professor Langtong from Cornell, Professor Bhattacharya, Malik, and Professor Loshi from Texas A&M. This work is motivated by the increasing DERs in distribution networks. DERs bring a lot of uncertainties and issues to the operation of modern distribution networks. The ultimate solution to address all these challenges is through expensive planning decisions. Essentially, system operators install energy storage devices, capacitors, or upgrade transmission lines, transformers, etc., etc. So the key question here that is the distribution network pushed to its physical limit? Do we really need these expensive investments now? Is it possible that we do something smart so that we never need this amount of money in the future? So all these questions are answered in hosting capacity analysis. Hosting capacity is usually defined as the amount of new DERs that can be integrated into a distribution network without causing any trouble. To compute the hosting capacity, usually people formulate and solve an optimization problem. Here we present a probabilistic version. The objective is to find the maximum level of DERs can be integrated into a network while satisfying all the operational constraints, such as disflow equations, nodal balance, voltage within limits, and line flow within limits. So here that the complexity that we have a chance constraint. We want the inner constraint or the operational constraint G of psi to be satisfied with high probability, at least 1 minus epsilon. Epsilon here is a tiny number like 1%. So this is a complicated optimization problem, mainly due to the challenging constraint here. So the key contribution of this paper is that we show that we can solve this optimization problem, this complicated optimization problem, using Bayesian optimization in a very efficient way, and we can find very high quality solution in a very short time. I'm going to switch gears a bit and introduce Bayesian optimization. Bayesian optimization aims at finding the global optimal solution to a very special form of optimization problem. The most interesting feature is about the objective f of x. The f of x function is usually like a black box. Sometimes we don't even know the analytical form of f of x. And f of x is expensive to evaluate in terms of money or time. So the goal here, ultimate goal here, that we want to find the global solution using as less queries of f of x function as possible. Algorithm 1 outlines all the Bayesian optimization algorithm, and this is one illustrative example. There are two key components here. First component is our understanding, which is a Gaussian process on the objective function f of x. So the solid black line and the blue shadow here model is our understanding. And the second component is the acquisition function that determines where we should query the next. Essentially, by constructing our modeling, the statistical model and acquisition function, Bayesian optimization iterate through the process until we get to very close to the global optimal solution. There is one little challenge here that Bayesian optimization deals with complicated objectives, but our problem has a complicated constraint. So one simple trick here that we can use penalty function to move the constraint to the objective. Then we can use Bayesian optimization. All the numerical results, all the numerical simulations were conducted on the 56 node feeder from IEEE, and everything is on GitHub. We are comparing Bayesian optimization with 3 state-of-the-art NLP algorithms: interior point, active set, and SQP algorithms. So there are 2 key findings in this paper. First, Bayesian optimization finds much better solution, 25% higher with much less, 70% less computation time compared with NLP algorithms. And the second key finding basically explains that why Bayesian optimization could find much better solution. So one sentence is that it explored the entire search space without confining in a local region like the NLP algorithms. So the top figure here gives you one example that NLP got stuck at a local optimal solution, while Bayesian optimization finds the escape from that trap, then finds the true global optimal solution in a very, very short time. then improve upon that. The bottom figure gives you some hint on some intuition on the exploration and exploitation trade-off in Bayesian optimization. So there are many interesting findings in this long work, and this paper is only the starting point. Please feel free to contact us if you have any questions or thoughts. Thank you so much. Thank you for listening. Bye-bye.